Thanks for the invitation. I'll be talking, I guess, a little bit about topics that have come up a couple of times, which is what's the point of the cosmic web? And so the first half of this is much more cosmology, and the second half is trying to say a little bit more about, what's in it for cosmology rather than what's in it for galaxy formation. Yeah? Okay, so the first half is work with Farnik, who is a student at Penn, but he's just started a postdoc at Yale with Nikhil Padmanabhan, Roya and Bruno in Paris, and Marcello, who's in Spain but is here too. Okay, so optimal transport. So the question is the following: we see objects for now, let's just say dark matter particles today. And so the dark matter particles today are these red guys, and they're in some clustered distribution. But the red guys came from some initial distribution, and in cosmology we think that the initial distribution was smooth. And so the blue dots are a grid, and in most numerical simulations they do start on a grid. And so, each particle has moved from its grid point to somewhere else. And so we're interested in figuring out, given that I saw the red guy, what blue grid point did it come from? So that's the question of reconstructing the initial conditions. And so, in principle, this red guy could have come from any one of these blue, and so there's some big combinatorial problem, and you assign a cost associated with big distances compared to small distances, okay? And if your only cost is big distances are bad, then you'll get what's optimal transport, okay? So it's a very simple assignment problem. And what's happened in the last, 10 years or so, is that computer scientists have come up with very fast codes for going through all the different permutations possible to sort through the list that will give you the set of assignments for minimum cost. Okay? So the initial versions of this kind of problem were explicitly an individual particle to an individual grid point. What's happened recently is they've been able to map this kind of problem in the following way. So they've been able to map what's called a discrete problem to what's called a semi-discrete, which is a discrete continuous problem. And the way it works is a bit like this. You say, I really want to get from red to its corresponding blue. But supposing I decided that my blue grid was finer. So now I want to know what set of blue dots correspond to each red one. And then I'll make it even finer, what set of blue dots correspond to the red one. And you take the limit of a very fine blue grid. And that lets you partition the initial space into the initial space that's associated with each red dot. And there are fast codes for doing this, for doing this partitioning. It's almost a Voronoi tessellation, okay? Okay. In this one, it's a Voronoi tessellation because I'm not moving the dots. But now if I ask, what was the center of this dot in the initial conditions, then it's a construction that's related to the Voronoi that's called the Laguerre cell, okay? And so the Laguerre cell, okay? And so this is partitioning space into the initial set of Laguerre cells that completely cover the space. And then once you've done that, you've then reconstructed the initial conditions, and you can ask, how does it correspond to a real simulation? Okay? I've set this one up in which each of the red dots is like a dark matter particle, and so the initial volumes are supposed to all be the same. So each particle is associated with an initial Lagrangian volume in space, which can, the initial space was uniform density, so volume is mass. Okay? In this case, each red dot is equal mass. So one of the steps forward in the last 3 years or so has been the capability of giving the different dots different weights. Yes, okay. So the real step forward is to not only compute the Laguerre cells, but to Laguerre cells where the dots have different weights. So semi-discrete with weights. For us, that will be, now each dot is like a dark matter halo. The dark matter halo has its own mass. All the masses are different. And now I want to partition the initial space up into, where each halo formed its mass from. Okay. A subtlety is that in reality, we're not going to observe all the mass. Okay, so we're going to observe, let's say, the most massive halos. And we're going to miss a whole bunch of other stuff. I'm going to call that stuff the dust. Okay? Typically, it's lower mass stuff that's below some observer's limit or some simulation limit. But that's going to be a complication, and I'll talk a little bit about that later. For now, let's not worry about that. Okay. So we want to do this, right? We want to figure out for each halo what was the initial volume from which it assembled its mass. Okay, and so here's the result of, you have a bunch of matter at redshift 0, and you're asking, what did it come from initially? And so, massive halos, they assembled from bigger patches initially, lower mass objects from smaller patches initially, and the dust is basically a uniform grid initially. Okay? And so, and then, this is the rule for, the mathematics, the thing that you're minimizing to define your Laguerre cell. And the case in which these are 0 is the Voronoi tessellation. And so, so these are the actual amounts by which the cells have moved. So one way to think of this is, what was nonlinear evolution? Nonlinear evolution was each halo shrank and moved. Okay? And so the shrinking is, this guy shrinks to become smaller, but in addition, its center of mass moves. And so it's Laguerre and not Voronoi because of that motion. So here's how well it does. For a massive halo, 10 to the 15 solar masses, 10 to the 14, 10 to the 13. Let's look at the massive guy first. The blue dots, those are all the particles that made up the halo at redshift 0 and where they were at redshift 0. The grid is those same blue dots, but where they were in the initial conditions of the simulation. And the grayscale is the Laguerre cell that you reconstruct from doing this optimal transport problem. Okay, so this is to show you that it sort of gets the shapes of the protohalos right. Okay. But, the center, so the yellow cross is the center of mass at redshift 0. The green is the center of mass of the the reconstructed, so the gray cell, and the purple is the center of mass of the correct initial center of mass. So what we're looking for is that the green and the purple sit on top of each other, and they may be displaced from the yellow. Yep. And so, in this one, it's not so dramatic, but for this halo, it happens that, the center is quite displaced. But the optimal transport algorithm has brought it back. So it is doing both. It's fixing the shapes and their motions. Yeah. You can kind of see it here. This proto-halo was long this way, but the final object is long this way. Yeah, and that's played into some of the things we've talked about. You know, you have bigger inflow this way to create your object by redshift 0. Yeah, and this was reconstructed even though there was no real information about any of the physics in here, right? The rule is very simple. You just want to move the entire set of particles by as little as possible. Okay, all right. Just to look in a little more detail, so here's another halo that's fairly massive, 10 to the 14. This is the same guy, we're just looking from, you know, the 3 different directions. Just to show you that, you know, the center of mass is quite far. It's moved quite a lot, but the reconstruction is able to bring it back to where it started. Oh, these lines here, they are what we use. So there's a outside here, so outside the halo, there are more grid points, which is all the other particles that were not in the halo. Those themselves are defining part of the tessellation, right? So those are making up, you know, the grids here. And so they're defining the boundaries. And so the boundaries are all basically complex polyhedra. And so that's just showing, you know, the faces that are going to connect to, you know, whatever's outside here. Right. Yeah.
These tessellations, they look pretty rounded, right? They sound to be, look to be convex or close to be convex. I looked at enough Lagrangian regions of fields, and very few of them actually that. Actually, they're fairly isolated fields, or the most massive ones in the box. So you need to have some kind of statistical description how well they describe it. Because very few of the Lagrangian regions are that nice.
So I guess we have, I mean, maybe it depends on the halo finder, but we haven't found really big issues. I mean, maybe you look at something like this and you'll say, well, this is actually a little rounder and this is making it too long. But we haven't really found things where there's 2 separate blobs or something like that. But yeah, I think as you go to lower masses, you get more of a mess.
We can discuss during the discussion time.
Okay. So we started this game because our goal was to use this for reconstructing the BAO feature in the correlation function, which is on much larger scales than these, right? These things are a few megaparsecs, if that. And so we started the project because we were interested in just undoing these shifts, the shifts of the centers of mass, and not really caring about the shapes of the objects. It's interesting that the shapes come out pretty well, but that was not the goal, right? The goal was the shifts. Okay, do I have the right page? Yeah. So this is a picture of the 2-point correlation function of the halos. The yellow is the 2-point correlation function of the halos at redshift 0. The dashed line is what linear theory would have been. So the way people derive cosmological constraints is they compare the shape of the dashed line to the yellow one. And then they're looking for, you know, it's not quite what they do, but they're basically looking for what is the peak of this and what is the peak of this. It's done more sophisticated, but that's the logic, right? You're comparing the dashed with the gold. Okay. The purple down here is the correlation function, the pairwise correlation function of the protohalos, so where they were initially. And so if you have reconstructed the positions correctly, that's what you're trying to get, is the purple. The green is what you do get, with this optimal transport algorithm, okay? And it's pretty good, and I'll come back to how pretty good in a second. The green and so the blue is another way of doing this, and this comes back to how we have to worry about the dust, okay? The fact that the dust, the stuff that's below the resolution, is clustered in some way. The blue is what happens if you assume that it's unclustered, right? So the U stands for uniform. The W stands for you put the dust as though it was in the cosmic web. Okay? All right. This is where you've done the correlation function of the halos, or the corresponding protohalos. You could mass weight each halo. The reason for mass weighting is a bit like saying the number of galaxies is proportional to halo mass, maybe to some power. And so it's a very crude way of showing you that this will work if you put galaxies instead of halos. That's on this one, okay? You can sort of see the amplitudes are bigger, 1.5 instead of 1. All right, so populating with galaxies, you're upweighting the massive halos more, they're more strongly clustered. Yellow, so again, the purple and the green are in good agreement. The reconstruction has worked well. Okay, we've checked endpoint statistics. So rather than doing bispectrum and stuff like that, here's one example. We're just looking at the voids. Void probability distribution, Eulerian and reconstructed. The gold is reconstructed. Underneath the gold is the actual protohalos. Okay, you can sort of see the protohalos better here. The Eulerian voids are all bigger. They were smaller in Lagrangian space, and the reconstruction has correctly reproduced what they were. Thanks. Okay. And so I'm optimistic for things like what Tom Abel will talk about for the nearest neighbor statistics. This kind of thing should work pretty well. I'm a little bit short on time, so I won't talk about this. What I'm interested for this one is to look a little bit at the shapes of the reconstructed correlation function. Okay. So let's look at this. The purple and the green are the protohalos and the reconstruction. So the agreement is telling you the algorithm has worked. But the purple and the green actually have a different shape from linear theory. Okay, and the way we're going to check that is we're going to say, if everything is correct, then the bias should have evolved. And so Jan mentioned the bias should evolve. We know precisely how the bias should evolve. And so this factor here is doing that correction. Okay, so the bias initially should be the late time bias minus 1. The Lagrangian bias is the Eulerian bias minus 1. Okay, so if I rescale the purple and the green by this factor, then I get the purple and the green here. They're, again, very different from linear theory. They're the right answer, but that right answer is not the linear theory shape. Okay? And so if you do reconstruction and you do it as well as you can, meaning you get the right answer, you will not get the linear theory shape. All right? And so the danger, or if you want, the gains to be had in doing cosmology, right? Because cosmology is going to be trying to fit this dashed curve either to the yellow without reconstruction or to this with reconstruction. And yeah, the peaks are all lined up, and so more or less you're going to be okay, but you could do better if you had a good model that you're fitting to the data. And so the quick statement is that we understand why the shape is different from linear theory. Here is, if we go through and we say that halos form from peaks in the initial density field, not in the initial density field, peaks in the initial energy field. The green is linear theory, the error bars are the measurements, and the red curve is what you would say for the peaks in energy, the sort of ideas that Marcello will talk about in his talk. Okay, and that one reproduces the shape correctly. Okay, and so if you want, you get a better template for the things that you're doing your BAO measurement with if you understand a bit about the cosmic web from which they formed. If you're doing things that you think are associated with peaks, then you're going to predict one shape. If you're going to go to emission line galaxies and you think that for them something to do with the fact that they're spirals matters, then you might start getting different features around here, and so better templates with which. So if you understand that, you might build of the energy peak stuff. It's very similar to the kinds of things that Christoph was talking about. And so if you want, you can ask me questions.
Chris?
Quick question. How does the energy transport algorithm you presented differ from Monge-Ampère-Klimantovich? Is it the same thing? Okay.
It is the same. So it's Monge-Ampère. The only thing is that it's the Monge-Ampère problem done with the semi-discrete rather than the discrete. That's all. Yeah. And I suppose in the literature, the other thing is that traditionally the Monge-Ampère was not done with particles having different masses. But with the semi-discrete setup, it's easy to give the different particles different masses. And so, so we were able to get the mass-dependent bias for free.
But Monge-Ampère-Klimantovich gives you a unique solution to a non-unique problem, right? In principle, on small scales, there's no unicity to going backwards. So if you apply it to BAO scales, I guess you're okay, but when does it break down, or do you see this?
Good, yes. So you can ask, here I've clipped at 25, can I go all the way to 5 megaparsecs, right? So we've done, so we've done things like that. I don't have plots here, I can show you. It doesn't work all the way down to 5, but it works close to 5, okay? And that's because we're working with the halos. So most of the shell crossing stuff matters for the displacements on 1 megaparsec scales or a few, but not much bigger. Yeah?
Your 5 is top hat 5?
Is top hat. Ah, good. So one of the things that I would have gone on to talk about is what's the smoothing filter, right? And so one of the things that happens when you set up peaks theory is that a bunch of integrals diverge if you use a top hat filter. So one of the nice things about Marcello's energy peaks is that you kill a lot of those divergences. And so that was a necessary thing to include. So we don't do Gaussian smoothing, right? That's the cheap way to get out of the problem, but okay. So okay, I didn't talk about that stuff, so I leave.
Right, thanks. It's really interesting. So question about the details of the assumption, where you mentioned that you basically assume the rest of the mass that is unbound in halos to be uniformly distributed, and yet when you look at
so that's the one that doesn't work, right? So that gives the blue. So that doesn't work.
Right, but what you assume then for the rest of the mass?
Right. Okay.
Maybe
So it turns out that you can do a very simple thing. So let me preface with the motivation and then where we are at the moment. The motivation was to be able to do this kind of reconstruction with minimal cosmological assumptions. So a very nice thing about it is the initial conditions being a grid is independent of cosmology. All cosmologies agree that's a good initial condition. Now, to put in a model for the stuff that's missing, you have to assume a cosmology. At the very least, you add up the masses you had a survey volume, so that's some mass density. You have to assume omega to decide how much extra stuff you have to add. So that's one thing you have to add. The other thing you have to add is, so if all you do is around each, so you make a grid that's 10 megaparsec, not 2 megaparsecs, but it doesn't need to be 20, okay? You make a grid that's about 10 megaparsecs, you estimate based on the halo that you have, what should be the mass in this region. So you use linear theory
expected
with bias,
density. Yeah.
Then in the cells that had more halos, you have more mass, you'll put a little bit more dust. So that's what gives you the green.
Right.
Okay, so you do put in some information about the clustering. So you have to have a prior on what the bias is of the objects you saw. You know that the sum of the objects you saw plus the other stuff, that bias is 1 because that's everything. So that helps you.
Yeah, thanks. It works incredibly well for the void. That's amazing.
The void works very well. Yeah.
Any other question?
I was wondering, so in the optimal transport, you just said as a penalty that you want to minimize the distance traveled by particles. Is there any scope to change that measure, like instead of being like the distance, take the the distance squared or that kind of thing to?
Right. So technically it is the distance squared. So
okay, well,
so it's the L2 norm rather than the L1 norm, but in principle you could put any power you wanted.
Okay. So is
it's
there
just
a way
that it has nice properties and convexity of potential and stuff like that.
Is there a way of like seeing it as a minimization problem of like minimal, like?
Yeah. So there's sort of 2 literatures in cosmology. So this one boils down to almost saying that it's the Zeldovich approximation. Okay. The other literature is what's called the least action principle. And I can crudely say that Zeldovich is everything went in a straight line, and least action is everything went in a parabola. So if I just say I want to parameterize not as straight lines, but as parabolas, and I want to fit for not the length of the line, but the 3 numbers that will specify the parabola, then you could do that. That's not what we've done, but yeah.
Dmitry?
Yeah. So that's right. Once you get a shape and you get a displacement which are almost Zeldovich displacement, but in approximation it is Zeldovich displacement. Then you have angular momentum essentially of your halo. Did you check how do they match with what you?
We haven't done any of that yet. Yeah. So
And of course it's 5 megaparsecs. So basically you have no shell crossing when your sigma is less like 0.7.
Mm-hmm.
And 0.7 is for us 8 megaparsecs for normal. So basically you could push your up to 8, and below 8 is becoming funny.
It's becoming trickier. That's right. That's right. Yeah.
Okay.
Yeah. Okay, I stop.
We can have one quick question and quick answer. Okay. Scott?
I'm just sitting here wondering is this pedagogy only, or you can run simulations.
So,
if I wanted to do the BAO properly, I would just have 1 million simulations and then figure out what the parameters are. So what exactly are you?
Well, one, you don't need to burn all that time, right? I suppose that's the main one. But the second one is, when you run the 1 million simulations, you also have to figure out what the bias is and all that stuff, right? And this one, to do the reconstruction, we didn't have to do any of that, right? We didn't assume anything about the tracers and whether they were peaks or anything. To interpret the results, we said, we had to know they were peaks to do better. But the reconstruction itself, we didn't need to do any of that.
Maybe psychologically friendly?
Thanks.
Yeah.